It's recording. I got my coffee so we can get started. Hi everyone, this is Research Jam 4. And as I announced on Twitter, I'm particularly happy this time because all our speakers are returning speakers. That means people are really treating this event as a lab event. They're coming back to show their progress. I think that makes me happier than any one-off events where usually the purpose is to attract new speakers. So we can get started. We have fewer teams this time, so each team would get more time. I would say 15 to 20, but because we have a whole hour. But do what you think that's the best. We'll start with Nigerian and Rohan. You guys go in turns, or you start?
All right. So yeah, I guess I'll just start. So hi everyone, I'm Nayan, and we'll be again presenting some of our updates from our project, which focused on poisoning the search space in neural architecture search. So the project is by myself, Nayan Saxena, and Rohan Jain, who's also presenting with me today, and Robert Wu. So first, some updates, I guess. So we submitted a 2-page student abstract to AAAI, which kind of improved upon our previous results. And we'll be presenting some of the results from this 2-page paper today in our presentation. And if you recall, we also presented a neural architecture type system, which dealt with how these architectures should be created and how layers can be replaced within architectures. So we also put forward a 2-page paper for that at AAAI. So these are student abstracts that we submitted. So let's move on to recap, I guess, like a brief summary of what we have, what this is all about. So basically, neural architecture search algorithms continually sample operations from a predefined search space to construct architectures that best optimize a performance metric over time, eventually converging to the best child architecture. So it's shown in figure 1 here, and networks derived from this procedure have shown very good performance on a lot of tasks like semantic segmentation, classification, object detection, and so on. Now, this solves a very, very big problem in machine learning, which is to basically figure out how to create, how to make the best, most optimal architecture to solve a given problem. Now, in our whole project, we are focusing on ENAS, which is efficient neural architecture search. So this basically uses the most important part about ENAS is that it has a predefined search space, which you can see on the screen. It is a directed acyclic graph. Now, this search space, which is denoted by S hat, was chosen very carefully by the original researchers who created ENAS in the first place. Another important point is the third point on the screen, which is that ENAS has shared parameters, which are trained using reinforce in conjunction with obviously an LSTM controller that samples child architectures. These shared parameters make it very hard for ENAS to decide to, like ENAS has no way of alternating between bad and good parameters. So if the search space is poorly chosen, then that presents an opportunity for an attacker to sort of inject bad operations and ruin the entire parameter space. So, and then there is training data poisoning, which has historically been a popular adversarial attack against ML algorithms.
Can I ask a question?
Yeah, sure. You can ask a question.
So when you say they have shared parameters on your previous slide,
yeah,
do you mean all the child operations? What's shared?
Yeah, so basically like the weights, it's weight sharing. So, so that, the efficient comes from the fact that instead of training the child networks from scratch, ENAS is training using these shared parameters. So it's sort of like transfer learning where there's already trained parameters that it uses from the previous epoch. So it doesn't throw away the parameters. and so it doesn't need to train each child network from scratch, which saves a lot of time. But that also is an issue, because if there's a bad operation or a bad apple somewhere in the search space, that sort of ruined like the optimization of the parameters, then it sort of presents an issue, which I was talking
So
about here.
cloud networks all have different architectures. How do they share? Or do you mean each component from the S head has shared parameters?
Each component has shared parameters, so that's how it works, basically.
Okay.
Yeah.
So you have like 1, 2, 3, 4, 5, 6, like 6 components, and they always have the same parameters. However, you piece them together into a shared network.
Kind of, yeah. That's how you can think about it. Yeah.
Okay.
Thanks. So that was ENAS, and then we have training data poisoning, which is basically you add a specific point to the training set so that it leads to high errors and poor loss optimization. So historically, this has been done against like SVMs and neural networks, and like a lot of like every year there are a couple of papers on training data poisoning. But this assumes that the attacker has access to the training data. And in our case, we are trying to now decouple the training data from the attack modality, which is the goal of our approach, which is search space poisoning. So basically, what we are doing is we are taking the carefully chosen ENAS search space and then injecting precisely designed ineffective operations within it. Now, this requires no prior knowledge of the problem domain or the training data being used, making this approach more favorable than traditional poisoning attacks. So next, so the most naive strategy that we presented last time as well was to just take a lot of these bad operations and put them into the search space. So if we overwhelm the search space with a lot of these bad operations, then obviously it has no choice but to sample the bad operations more, leading to a higher error. We reran some experiments with this multiple instance poisoning framework as well, some of which you can see on the screen. So we had a few operations, like we had identity layers, we had Gaussian noise, dropout, and transposed convolution. Dropout is with P is equal to 1, by the way, so it's complete dropout. So if you see, in order to be effective, our multiple instance poisoning approach requires up to, if you see 50, like if you see the highest point is at around 50 in each graph, which means that it requires around 300 operations to be injected into the search space, because 50 operations per good operations means 50 times 6, which is 300, which is a big number. And we had some criticisms earlier from Roseanne and others who kind of told us that, it's unreasonable to expect that, you inject 300 bad points and the algorithm functions proper as it's supposed to. So now our entire goal shifted to reducing this number to as much as possible, and we've made that happen now with our one-shot poisoning approach, which Rohan will talk about now.
Just one quick thought here.
Right.
You could almost take the results from that first part of the study as an interesting conclusion, because it shows how robust ENAS is to adding a few bad operations. Like I would have actually thought you could break it more with only half bad operations, but here you need like 98%, 99% bad operations before it really breaks, which actually speaks to the power of architecture shapes.
Yeah, some operations although did well. I mean, if you see Gaussian noise, it required a few of those to even reach beyond a 50% error.
Yeah.
But some did poorly. So it depends, I guess. But yeah, that's a good conclusion to draw.
Yeah, but you should even, if you imagine wanting to write that other paper instead, you would really want to zoom in around 0. So 0 is the baseline performance. 1 is half the operations are noise, or half the operations are bad, which is already a very strong unit of noise. And like it looks like it still kind of works there, like 0.2 goes to 0.5 or something.
That's correct.
But how do you claim those added are bad operations? Because dropout can be good for some architectures, right? Although you're using 100% dropout, but identity like could be nothing.
Identity could actually be fine, right.
I mean, not all of these are quote unquote bad operations, but the logic was, I mean, with identity, our reasoning was that doing nothing is like, if you make it do nothing more amount of times, I guess, then it's going to like possibly harm the performance.
Do you train those operations? If you train them, they might do wow, right? They might add value to the architecture with it.
So certain operations do add value. So we studied before, like adding like dilation layers were adding value to it. Like that was in fact improving it. But so these are not exactly the name, we call it bad operations, but it's just like more like a poisonous or like an ineffective operation. It's like you have the good operations which ENAS already defined, and then we have these ineffective / bad / poisonous operations which we introduced here. So depending on the type of operation, like so these in particularly were not very like on their own they're pretty effective, as in like they do the role of killing ENAS, but as you said, like some operations could be better than others, and what we saw was dilation was actually helping us. It was improving ENAS, so that was a more good operation instead. So that could be considered possibly to be an operation in the original ENAS search space.
Right.
And now,
I don't know if you describe maybe a version where you don't train those operations, you don't train those ways, and just fix them at initialization, so they're guaranteed to be worse than the version where you do train them, and then to see if there's a difference in performance.
Yeah. So yeah, that could be considered as well. I mean, from what we've been like trying as of now was that like with this multiple instance framework, and where we got all our criticism was like, if you saw in the slide before, what Nayan mentioned, like over here, like we injected like the search space with up to like 5,000% of like the original like search space, right? And I think like you also mentioned like that's like a flaw, right? Even though they do this similar like style in like traditional data poisoning, in traditional data poisoning, they're taking like 8% of the entire like MNIST, for example, or CIFAR 10, but that's 8%. But now in our case, we're taking ours, we're not dealing with that, right? Since we're dealing with a more data agnostic approach, we're dealing with the search space itself. So the search space is already very small, right? So adding 300 points to the search space of something like a 5 to 7, right, is like a huge value. So it was completely unreasonable, right, to expect the controller to even sample those good operations when like the ratio of like bad to good is like much greater than like 10 to 1. So now our goal has shifted to injecting the original search space as had with less than 6 ineffective operations. And
I think it's a good transition in the project. I do think you should be careful when comparing poisoning based on specific data points to poisoning based on bad operations being added to the search procedure, because data points and operations in the search procedure are not the same. You might not even want to call the operations data points or like points at all, because they're kind of quite different. One is
you shouldn't call them points.
Descent, one is used not. Also, can you go back to the graphs for a second? So, for example, here adding transposed convolutions, or you mentioned dilations in another part. These are operations which like obviously can be useful in some networks. So it's not like this single operation, unlike say dropout with 100% dropout rate. It's not like this single operation is on its own poisonous or even unhelpful. So I think it might help in this part of the project to separate. There are kind of two ways that you cause ENAS to fail. One is by adding operations that just hurt like any network. And the second is by overwhelming the search procedure with a specific single choice, which, while it could be useful some places, is not needed every single place. So for example, transposed convolutions adding a single option, so instead of 6, you have 7, it's probably great to add a transpose convolution. But adding 50 transpose convolutions overwhelms the search procedure. You could test this by going back to the original ENAS, and taking all of their operations that are presumably good and replicating the same experiments. So add one normal convolution per other operation. And so overwhelm ENAS with just normal convolutions. And you will see a kind of similar curve, right? It's gonna be worse as you like bias the search toward only ever choosing normal convolutions or only ever choosing skip connections or whatever. So that'd be a good baseline, I think, for this part of the paper.
Mm-hmm. Yeah, definitely. I think that one of like some of the tough questions that we came across, like as you said, like transpose convolutions are usually like good, right?
Mm-hmm.
And it's pretty tough to answer. Like in this case, like I mean, fine, we are throwing like 300 points at it, but like as you said, right, a transpose convolution is usually meant to be like effective, right? Better than a standard like convolution. So why like its effect on poisoning is like why even with like initially like the first point that you see, right? Like even that's like having nearly like 40% errors. So like just by throwing like
which first point? The one at
the one like in the bottom right, like the one that the cursor is on like on.
But that's what is that?
That's
6?
8 or something. Yeah, that's already.
Yeah. Wait, that's per original operation. So that's
per
8.
Original.
So that's 6
so
original
like,
plus 6 times 8, 48.
48.
Yeah,
So
yeah.
That's already like very, very far in the you would never do this on purpose if you were trying to get the network to work. So I think the most interesting points are maybe going to be 0 versus 1.
Mm-hmm.
But there's even another point. It's 0 versus 1/6 or whatever.
Mm-hmm.
0 versus we added a single transpose convolution. Is that better or not? And I would guess it's like 50-50. It could be better, could be worse.
Mm-hmm.
I see. Yeah, that's interesting to consider. Yeah. Actually.
Isn't there a point where it's only one?
Yeah, that's like the second dot. Like if you see, like that's like 6.
Yeah.
Basically, yeah.
It's 6 transposed there.
It's 1 per, which is 6.
One per, which is 6.
So it's 6. So we started with 6 and then we went up to 300. If you look at just the numbers, that's how we did it originally. But now we actually improved it. So I guess the next results might be very interesting to all of you because
David asked us a question in the chat. Also, you guys take a look.
I was just going to very quickly ask these graphs. As I may have got this whole project mixed up, but it's trying to find the best. It's trying to optimize the architecture, and these graphs don't have like an architecture parameter in them that I can see. So is this at the end of the search, and this is the best thing the procedure has found?
Right. So these graphs are not across like the whole training. Don't show the entire training process. This is just the final accuracies that you see on each dot is a final accuracy that you see, or error. Sorry.
Okay, so if I understand correctly, in theory, they could all achieve the same maximum output, even with a huge amount of error, if they had somehow focused in on the best architecture that's still available from the layers. So that's like an interesting result then, I guess. Yeah, cool.
Yeah, because ENAS, so that's what we found is that, the sampling process that ENAS uses is not very efficient, is not very it doesn't choose A versus B. So it doesn't look at the bad, it doesn't see when something is wrong and sort of starts rejecting it even more, which it's supposed to do kind of, but in this case, I guess because we overwhelmed it so much, it wasn't able to do that. And also we looked at some of the networks that this created, and most of them, the final networks had all sort of the quote unquote bad operations in it. So if you saw a final network from multiple instances, you'll find that it has like all identities or like all bad, like all poor operations in it. So that's possibly one reason, but yeah. That was
We're talking about how identity could kind of be useful, but we're overwhelming it with 300 and that's unrealistic. But maybe it would be interesting to say, well, if we do have 300 identities, but we have 300 useful operations as well, does it still get trapped in the identities when we're just giving it a very big search space, but not necessarily an unfair search space? That might be interesting.
That's fair to consider, yeah. We have not
you can kind of see that actually in this, because if you see the very first, I don't know if you can see my cursor, but if you see this point here, right? This is 6 identities and 6 good operations here. So it's kind of sort of doing a similar 1:1 ratio, which you are trying to talk about. Although not 300, obviously, but this here has 1:1 ratio between good and bad operations.
I think what David was suggesting is take the 6 original operations and copy them all 10 times. So now you have 60, but the ratio is still correct. So it kind of like pushes ENAS closer to random architecture search. So you still find the same stuff, and you're not even biasing it toward convolution or toward skip connections or whatever, but you are prohibiting it from learning that like one convolution is the same as the other convolution. So it's got to sample both and learn both separately.
So basically changing the original ENAS search space to make it more balanced. So you have like equal on both sides.
It's already balanced, right?
But like now we're going to be increasing the original size of the search space, right? Because he's suggesting
baseline is ENAS with 6 operations. Treatment 1 is ENAS with 60 operations, where each of the 6 original is copied 10 times. So the ratios are the same.
Yeah.
But it's got a bigger search space. Like, does a simply larger search space hurt ENAS a lot? That's the first question.
Makes sense. Yeah.
Second is, does a biased search space with good operations hurt ENAS a lot? So that's like 1, 2, 3, 4, 5, 6, and number 6 you replicate 100 times. Third question is, does ENAS with very biased sampling space and biased toward garbage hurt ENAS? And the answer you've shown here is yes.
All right. Yeah, so I mean, I guess we can look at one-shot results now. So Rohan, you can talk about
so now like, so after the multiple instance, right, we thought like, how can we possibly like reduce the total number of like operations in that poison search space? So we came across like 2 actually, just again simple straightforward operations, but we injected only 2 additional poisonous operations in the search space: the complete dropout and like a stretched convolution with like kernel size like 3 by 3 and like padding and dilation equals to 50. So we thought that maybe this will have some effect. So you see that now in this table that when we're getting basically 90% error just with 2 operations in the search space in the search space. So now we have a total of 8, the 6 plus these 2. So actually like the dropout and the stretch convolutions weren't that effective on their own. Like as you see in the second row of the table, like even when we injected like previously from multiple instance, like when we injected it 300 like dropouts, we only got like around 84% validation test error. But now with just 2 operations added, a stretch convolution and a dropout, we're getting 90%. So we injected exactly like 1/3 of the original size search space with bad operations.
So in the third row here, what happens? Does ENAS choose the stretch convolution only or dropout only?
Yeah, so we'll show that in the next slides. Right. Like we generate like architecture. So this is just like, again, like some results. Basically like validation error like for one shot, like it's basically average of 3 runs for a total of 300 epochs. So you see it's again like fluctuating in that like 90% ballpark. And then on the right is like the number of bad operations in our final network. So we have this more like uniform distribution looking plot. In the next few slides, we show, I think in the following slide, yes, this is the slide that we were basically saying. So this is like one of the final architectures that we drew out. So in red is bad operations and in green are the good operations. So in total, like in ENAS, like for each network, there's 12 operations. So like you can see directly over here, it's like 1:3 ratio. We're actually, so it's sampled, I think it sampled 2 stretch convolutions and a dropout. And the other 3 are just like from the standard ENAS search space.
So what can you say what stretch convolution is again?
So a stretch convolution is just like, again, it's a standard convolution with a padding and dilation with 50.
Okay. Is this MNIST or what is this, CFAR?
CFAR 10.
Okay. So what is so dilation 50? So that's 3 points, like 0, 50, and 100 kind of.
0, 50.
Very stretched out. So
Very
why should that like ruin anything?
I mean, that's like that's the question we've been
That's exactly what
stuck on.
We are stuck on right now, because so we did this, right? And we also ran them individually. So we ran ENAS just with stretched convolution, and that did not make anything worse. And with dropout, as you can see, it required like 300 operations to even reach some high error rates. So individually, these operations are pretty good, but for some reason, one dropout and one stretched, like one convolution like this is causing this effect, which we are trying to still sort of understand what's happening.
Are you using like same convolution or valid convolution? Like, does it go to the edge and into the padding region or not?
Sorry, can you say that again?
When you make the conv layer, you have to specify, does the conv go just to the edge of the image and stop before it gets into the region beyond the image, or does it continue beyond the region of the image so that the output is the same size as the input? So like if you have a 100 pixel wide image and a conv with a receptive field of size 3, either the output will be 98 pixels wide, because the 3 goes to the edge, slides to the other edge, but it doesn't slide past the edge. That'll be valid. Or the same option will give you output of 100. So it'll go beyond the edge 1 pixel left and 1 pixel right, so that the output is the same size. The point is, for dilated convolution, if your dilated kernel is, in your case, 100 pixels wide, or maybe 101, I'm not exactly sure, then the valid convolution will either give you like a null output or maybe a single pixel output, which would probably like destroy all information about the image, or nearly all information about the image. So if there's no path through your network that's not through this specific layer, it's basically just like deleting the whole input, and then the output is just random. Like the class decision is not based on the input at all, which would produce a 90% error, which you do observe. But if you go to your architecture, it does look like there's paths through the network that don't go through the stretched convolution. So like if you go input to the first conv3, and then you jump all the way to average pool, and then you jump all the way to the end, like that should be a path, a normal sane path through the network, which could be trained. And if so, it should produce error way less than 90%. So I think you should figure out what's going on. In particular, if you just plotted your network, printed out the representation size of each layer, you might see that it collapses to 0, like some weird, like literally no representation, or maybe 1 pixel, which isn't enough information. Although even 1 pixel should give you better than 10% accuracy.
It's a little tiny thing. Are you guys using ReLUs in this?
ReLUs, I think we are, right, Rohan? We are using softmax.
It's more softmax activation at the end. In ENAS, they have a softmax activation layer at the end.
Okay, just because if you're putting like crazy weights through it, maybe the ReLUs are dying, just like a tiny idea.
We're adding crazy. Okay.
Could. In general, if you see training error that's not any better than chance, you should be like a bit suspicious, or like you're not just in a we chose an architecture, but it's pretty bad regime. You're in the thing isn't even starting to learn anything regime, which it just means something's broken outside of what was broken before. So you should consider like what regime you're in of how you're breaking the network.
Yeah, we've been trying to figure that out for a while, and we had to delay. Like we were planning on submitting like a big paper to AAAI, but then we saw this happen, and then we couldn't explain it. So we are being patient and trying to sort of see what's happening here. I
would try to dig deeper and understand what's happening, and then a separate factor, no matter what's happening here, a separate factor is, since train error is so bad and val error are so bad, why does ENAS not like steer itself in a different direction? Like it looks like adding this network layer breaks the network, so ENAS should have tried something a little better.
So that's why we started drawing these controller like probability graphs, just to see how many sort of bad operations it's sampling, and it seems like it is sampling a few here, but not as many as some of our other search spaces where this was kind of skewed to the left.
How did you make plot B?
So for plot B, we collected like at every epoch of training, we collected the number of good operations and bad operations that were sampled. Like that were sampled within a child architecture, basically, that was sampled by the controller. And then we used aggregated all of those numbers and sort of got a density from that.
How many networks go into this? And is it a histogram or a kernel density?
I would say it's 300 because we only chose like one per epoch. So it's like one network per epoch. So it's 300 networks that go into this because it's 300 epochs.
And so this is literally 300 data points.
Yes.
And then did you make this plot using the histogram function or using something else?
Histogram? No, I didn't use histogram. I used a Seaborn density plot.
Okay.
Like Seaborn has a
okay. Which smooth thing? Now?
It's a KD kernel. It's kernel density estimation sort of a thing.
Yeah. I got it.
Yeah. So we were trying to see, what's going on under the hood, but as for other search spaces, even we didn't show you the graph, but it's pretty skewed to one side. Like the number of bad operations is very high.
Yeah, I think in the following slides, you can see that, yeah.
Yeah, we'll show you some results in the following slides. So we ran some other experiments. Rohan, you can explain this part as well.
So again, this is like, again, similar, like, again, we basically tried to just see if like a multiple instance framework under this one shot, like would still apply. So again, this is just like demonstrating like the probability. Well, not this graph particularly, but again, just like the 90% error when we've injected again, like, up to 300 data points, like in 3D. So again, you're getting in that 90% ballpark. But in the following slide, if you see, this is where we see like these graphs demonstrating like the probability of like the controller sampling bad operations over like the 300 epochs. So I mean, in 3A is like when we just have 6, right? 6 per like just 6. This is like the first instance. So actually 6 extra operations thrown. So this is getting similar look as like the previous results, where it sort of has that uniform look. But again, as you increase the number, like the multiple instance value up to 3D, you see that the controller, like it's very much skewed. So it's like literally sampling like only the bad operations in space 3D.
Is 12 the max bad that you could ever have?
There is 12.
12 is the 12 is the size of the network. So network can only have 12. So it's pretty much comprising of all bad operations, basically.
And what's space 3B? What is that comprised of?
3D is okay. So yeah, I guess Rohan kind of skipped over this part, but this is basically we use the same search space as before with those two operations, but we applied the multiple instance thing. So 3A is basically six of those that basically points, and then 3B is
36.
I guess 36 and so on. So 3D would be 300 again in this case. At least this is just an experiment we ran to see what's happening. And this is something we saw, and we are trying to sort of see what's going on. So it seems like the controller is getting confused or something, but with the less number of points, that it's not able to throw them away and just focus on the good ones, which is very interesting. So yeah.
Cool. I would definitely dig deeper on like that. Pick one network with a specific architecture and just dig a little deeper on why it doesn't train at all. To do that, you could print out, like put a breakpoint in your code, print out one batch, training loss in that one batch, and then run that same batch again, run it a couple more times. If the network can't even decrease the training loss on a single batch with repeated exposure to that batch, then it means like the training's broken more than normal, and you should know why. I think, Roseanne, I don't know about time, but probably we should.
Yeah, these were all our results pretty much. I think we are done. Yeah, there's just some next steps, but we already discussed a few of these. And yeah, we have code that's publicly available and we can share it in the chat. Yeah.
Awesome.
Cool. We can move on to Mishka.
So last time I had this request for plot to try a different attention formulas in transformers. And of course, this requires transformer training experiments, and those are supposed to be expensive, and it's always a problem. But what's great about requests for plot is that you get rapid feedback from many people. And I got nice feedback from many people here and even elsewhere. And one of them pointed me to compact transformers and to this nice paper, Escaping the Big Data Paradigm with Compact Transformers, and which has open source implementation. And they tweaked transformer architecture and did few things with it. They obtained things which work for very small data set like CFR, and even small transformers like with only 300,000 parameters works not bad. And if you add more parameters, then you start getting nice state-of-the-art results. And
that's good to know.
Right, and that's my main goal of today present. I will update you on my request for plot, but my main goal was to share this, that if you have ideas for transformer changes, this might be a nice, so my runs took typically an hour on laptop, on home laptop. But they even claim that 30 minutes, but maybe they're small configuration, or maybe who knows. But they have a variety of configurations. So I created even a fork because they keep changing. And so I fixed the version which I worked with. And so my main goal is this. Now I'll tell you what happens with my RFP. Results are inconclusive. I did not run as much experiments yet as I should have. The pure version led so far to modest degradation. But then I recalled that I also had this idea of remixing the original values with cross-normalized. And the original motivation was to fix to cut training time, which is not any more relevant. But some of our experiments with images made us think that softmax is good, but losing balance between negative and positive values is bad. And it would be nice to keep both. And and when I started to do this, I started to get very, very mild improvement, but I don't even know if I need to run more runs because it's so small, and training runs, of course, differ because of initialization and stuff. I need to even do more reruns to see that even this small improvement is actually true and not a fluke. But of course, it's also, I'm not sure, so far it might be not good enough for a paper, I don't know. But there is quite a room for search of modes. And here I sort of kept in this directory which has also the slides. I kept log of my attempts.
Hey Mishka, can you remind us? So the normal transformer, you're using the values V, a matrix of values V.
Yeah, right.
In your case, you're taking softmax. Like, which dimension is the softmax over?
Softmax cross. I take vectors consisting of all coordinates of values. I'll take. Let me bring the previous slides up. 1 second.
So if you have an input sentence or an input image or whatever with 20 different tokens, it's like a softmax over the 20 positions, right?
Right. No, it's a softmax of how many. Yeah, if there are 20, it's the cross normalized softmax is this. I take the fixed position for all values. So you take how many values.
Oh, okay. So it's over channels.
Yeah, over channel.
I see. Okay.
Cross normalization. It's orthogonal, right? So that's right. And that was because I let me unshare this one maybe and share a Jupyter notebook for a second. If I have time to share a Jupyter notebook. Right, so if you multiply monkey by monkey, you get something like this. And if you multiply aircraft by monkey, you get something like this. But if you softmax rows of the left matrix and columns of the right matrix, then you are getting more interesting picture like this and like this. But now let's do something else. Let's normalize images so that they're not that the values of points not between 0 and 1, but between -1 and 1. So black is not 0, but -1, and 0 is gray. Then you get these results. So see, you have this also gives you some nice improvements. So this tells you that it's nice to keep balance between positivity and negativity and keeping both. And that's why I thought keeping both. And yeah, I keep this log of my attempts, but I need just to run more experiments to say more clearly what's up. Okay.
First of all, you shouldn't run everything on your laptop. We can sponsor you some compute credits so you can spin off a computer and actually run it properly.
Thank you. Thank you. I'll write you. Yeah, that might be, yeah, because then I can run in parallel many things. Right.
And second of all, I like the mixing idea. So I think it's always a good validation if you set alpha to 0 and to see if they reverse to the basic transformer. And also, what's the main idea behind compact transformer? How do they make it compact? You know?
They did a few things. I tried to read the paper, but they did some new type of pooling and brought some transformation in. But yeah, my understanding is not good enough to present it well. I've read it, but I sort of thought, okay, looks like it makes sense. Let's see if I can reproduce what they say or whether it converges to what they say. And yeah, it seems like so. And then other people seem to implement it. And, but my understanding is not very good, so I can present it right now.
Yeah, we can also all read.
Yeah.
You mentioned that some values of alpha work better than I guess alpha 0, which is the normal transformer. Like which sorts of alphas did you find that work well?
I mixed 1-to-1, and but it's not quite honest 1-to-1 because the range of data was from -3 point something to 5 point something, and the range of softmax data was like from 0 to 0.3. And so I either added softmax or I subtracted. When I subtracted, it was more interesting. It brought it closer to balance, but the training became less stable and sort of giving more improvement on one run and then drop on the other. It was so something is going on there. But so I tried.
So I think one thing you could try is first separate. So you mentioned adding versus subtracting. Separate the sign into one separate experiment. So run experiments where you use only positive signs. So you're adding, and then alpha from 0 to 1, and just plot maybe 10 points along alpha 0 to 1, and either it's going to be the baseline alpha 0 is best and then it just gets worse, or it's going to get like same flat, or it's going to get better somewhere.
Right.
Do that for positive sign, show all the alphas and how well it works, and then try negative sign, make the same plot for negative sign. If you subtract with alpha 0.3, 0.4, 0.5, is it getting better anywhere? If you somehow find that there's a point on that plot that's reliably better than the baseline, then that's a very interesting conclusion. So you'll have to do enough runs to have like little error bars. And if like you're saying it's better sometimes, worse sometimes, and then the error bars are really wide, fine, just show that on the plot. We'll see if that's the case. But like that's the experiment you should run.
Okay, then I'll write you for some compute access because that is a bit too much, because I want to run in parallel. Then
you got to run all 50 at once, exactly.
Right. Yeah. On laptop, unfortunately, it's not like this.
Wait, does your laptop have a GPU?
It does. Yeah, I don't know if it's a good one, but I don't know even if. I sort of tried to turn it on, but I don't even know whether. I mean, like when I reinstalled PyTorch for this experiment, and I hoped it picked, but who knows? Did it pick or not? I didn't check.
Yep. Well, hopefully GCP or something will be much faster.
Okay. So I will write your Razan and ask how.
Yeah.
Okay. Good. Thanks.
Talk about that. Cool. Now let's move on to Stephen. Hi, Stephen.
Hi, Wilson. All right, so during the last research jam, I talked about a project I worked on, which is a prototype that can detect sign language meanings in images or videos and generate equivalent voice of words that is being communicated by the sign language. Yeah, so, and I also talked about my next step, which is to retrain on TensorFlow object detection API, using a better architecture. I also talked about increasing data set range to support more than the initial 50 plus sign phrases. And I also talked about writing a paper on it. Yeah, so thanks to all the support during the last research camp, so I was able to gather up enough nerves, to go along and work on the paper for this. Yeah, so this is the paper title, and it's simply trying to understand sign language, using the edition. And here's the synopsis. Well, it's a research paper now, so I had to do lots of, background research. So I discovered that about 5% of the world's population has hearing disability. That 5% is around 460 million, I think. Yeah, and each chunk of this population appears to come from sub-Saharan Africa, right? And it's also a little bit ironic that sub-Saharan Africa being the largest within the region with the most cases of hearing disabilities seems to have very little or no resources at all when it comes to sign language solutions out there, especially using artificial intelligence to translate sign languages. So the whole synopsis of this project is to develop a lightweight sign-to-speech machine learning application that works in real time to reduce the communication barrier between the hearing impaired community and the larger society. I mean, I actually visited some of the special education schools, and it's quite obvious that it's going to be a little bit difficult for this hearing community to integrate with the larger society, right? And of course, there's going to be this social awkwardness and isolation, and of course, they can't really take up positions in the larger community because of this very important disability, because communication is key to almost every other facet of woman's life. So the first thing I needed to do was to create a data set, using Nigerian Sign Language as a case study, as Nigeria is one of the many countries in sub-Saharan Africa. And of course, there are very little. In fact, when it comes to Indian science, there are no resources. There is no resource out there currently, right? So that means I had to create my data set from scratch. Yeah, so I was able to, create a data set with the help of a sign language TV podcaster in the state where I reside in Nigeria. And after that, I decided to, scale it up, and I met with teachers from two special schools in cities in Nigeria, and the teachers alongside their students with creating a much larger data set for this purpose. So currently,
wait, so they
about
you
okay.
you like recorded them in class doing different signs or what?
Oh yeah. That was what I did. I recorded them in
That's cool.
in the classes, performing science. Yeah.
That's cool.
Okay,
That's cool.
so going. Oh, thank you. So we have about 8,000 static images of 135 plus sign words and phrases with 20 plus individuals. And of course, the images were captured in diverse backgrounds to account for the different environments in which the application could possibly be made use of.
Do you know how
Annotation
much?
was.
Do you know how much
Okay.
the interpretation of a sign depends on just like one frame of the sign versus the motion of someone's?
Yeah, that's actually true. Uh, some actually, series of sequences of different signs. Yeah. So, and that's, I mean, if we're planning on, making use of videos instead of images, we need to account for uh, a very large, computational power, and this is a private project, it's a personal project, so I'm not sure, we'll be able to do that. So what we resorted to doing is to capture the key moments in each sign phrases, in each sign phrase. We realized that most of these signs, they all have a particular moment that is, that is key to that particular sign. For
So you include only these like key,
yeah.
like the best one frame in the data set.
Yes, that's what we did. Yeah. So
okay.
we try to capture the key moments and use the key moments for the training.
Okay, I think that.
All right.
I mean, I would love to see how that worked. I think that could potentially be tricky because if you imagine you train a big model on this and the model works pretty well on the training set, then you have a model that can detect really well like key moment. I don't know what the sign looks like. Key moment here, key moment here. But if you run it on a live video stream, then it might get the right answer at all the key moments, but then all the frames in between, it might A, not know that it's not a key moment, and B, it might say something kind of, it has to make a decision. It'll say some other class. So it might be better rather than training on just one key moment frame, like train on a kind of wider region so that the model has exposure to like not only the key moment, but all the frames nearby the key moment. And it could kind of try to make the same decision, if that makes sense. But I would love to see like how it works as is.
Okay. Yeah, thank you. So the images were annotated using Libel IMG, and Libel IMG is a graphical image annotation tool, yeah, for images. And because I planned on training in with two architectures, so I had to label the images in YOLO and Pascal Voc format. Actually, I only labeled in YOLO format, and then I wrote a script to convert the YOLO annotations to Pascal Voc annotations. All right, so I trained the first model on YOLO MIF5 model, right? And Oh yeah, so I trained across 81 epochs. I actually wanted to train for longer, but I was using Google Colab, and Google Colab is designed for interactivity, right? So I can't just leave it alone for hours or days, without tending to it. Yeah. So I think the 81 epochs on for about 6 hours, and I had to sit in front of my laptop throughout, the training sequence. Yeah. Okay. So there are lots of these are just, uh, or the hyperparameters or settings, and yeah, any other information, about the entire training. So the image size was, 640 by 640, and yeah, so there were 135 classes, and of course these are some of the examples of the sign words. Also, okay, yeah, looking at here, most of these uh, manipulations on the data, especially the ones below here. Uh, they are all data augmentation techniques. For example, this is HSV manipulations, and HSV is simply talking about hue, saturation, and value, right? And there is scale. Scale is just, zooming in and out, and there is flip left and right, and yeah, so basically I did some, some data augmentation of processes on it, right? Not just to include not just to increase the entire data set, but to account for instances, uh, where the where somebody performing the sign might be, zoomed in on or zoomed out on, or maybe the entire environment is darker than normal, right? Yeah. So that was the main idea behind the data augmentation. So yeah, so after training for 81 epochs, and yeah, so I was able to, to have a report score of 0.99. Yeah, but the precision score is around 0.62. And yeah, what Jason said, I think that's played a part in here. Yeah. Um, the fact that, a particular key moment might actually be part of another science sequences. Yeah. So I feel that might have, affected the model performance a little bit. One other factor that might have, affected the precision is when I deployed the model, just to check how well it's performing, I realized that it has a little, it's a little bit fond of imagining science, uh, at random shapes. Yeah. Say there's a dark corner here, and you could just imagine that, okay, that looks like, thank you, or that looks like smile, yeah, so that was the situation. But I was hoping that, maybe once I'm able to train for longer, it's going to it might, increase the precision, to some certain extent. All right. Okay, yeah, so some of these are some of, my evaluation, um, and I think generally it did well. Yeah. Though I also noticed that the cases where, it got it wrong, for example, over here, I don't know if you could see this. This is the actual labels, and this is the predicted labels. But over here, this is A and this is A, but it's interpreting this as X, and it's having 0.3 certainty. Yeah, so I think that 0.3 certain. Well, generally, when a model has is predicting a very low probability score for a particular class, there's actually a strong possibility of that prediction being wrong. So I think that's the same case here. And also, well, generally, it did well in recognizing, this sign was right. Yeah, even when, they don't look the same. This is I love you, but the shape of the hand is sideways. But this is also I love you. and this is, this is quite, displayed more prominently than this, but it was able to recognize this. And for somebody that might not be vast in sign languages, you might possibly feel that this "I love you" resemble is, right? But the model was able to, to recognize this "I love you" perfectly. And I also feel this also might be due to, the position of the ends, on the body, right? I'm not sure if you could see this, but this is actually on the chest. And most times when people when people perform these signs, this "I love you" sign is most times around the chest region, or they're displaying their hand, prominently. Challenges that I faced. Oh, I should also mention that the SD model, I mean, the single state detector model is still in progress. Yeah, and yeah. So talking about my challenges, the annotation was quite stressful. I mean, very stressful. I had to annotate about 8,000 images by end. And yeah, that wasn't a joke. And also, the model cannot capture sequences of spelling. For example, there are some words that you can't, there are some words that don't have their sign equivalents, and you need to spell them. For example, if you're referring to a location, say Nigeria or New York, yeah, you need to spell a word. You need to spell a word like that, right? And even the name of people, yeah, all very, very rare words, very rarely used words. Yeah. So this kind of words, you need to spell them. But, the model will be able to say you're spelling New York, spell, then N is going to come first, E is going to come second, then you have your Y space, then you have your Y, Z, Y, O, R, right? But the model won't be able to, capture this sequence. It will be able to get N, to be able to get new E, W, right? But it won't be able to chain that sequence of spellings together. So that's a that's a particular con, uh, when it comes to using this particular model. And yeah, this is also a bit of an issue for me because I was using Google Colab for my training, and yeah, so the compute resources constraint was actually, a big deal for me. Yeah, so my next steps currently is to, at the first is finish training the SSD model and compare results of the SSD model to the YOLO V5 model. And also I want to finish write the camera ready draft and submit to the ML for Developing World workshop at NIT. Yeah. So the deadline is Saturday, this coming Saturday, but I think I'm quite, confident that, I'll be able to do that too. Yeah. I'll be able to, pull that through. Yeah. Okay, yeah. So I'm thinking of graduate school, and I think this project has to really think of chest. I believe that, I enjoy mentioning important, not necessarily for social. I mean, I like the fact that this is targeting a problem in the community, but generally, probably due to my uh, very strong technical background, engineering background. Yes.
Oh no, maybe we
yeah, I think he just
lost him.
no, it's back on. You're muted.
You're muted, Stephen. Welcome back though.
Oh, okay. Yeah, sorry about that. Okay. Yeah, so I didn't know where I leave off. Maybe you could remind me of where I stopped.
You were just wrapping up. I think this is really cool.
Okay.
Stephen, could you say more about I didn't understand the spelling part. So it seems like your model, if you recognize each character, that should be fine. So you could just spell out New York. Is that the goal?
Yes, I can spell it out, but it can't. It's not intelligent enough to recognize that. Okay, we are trying to spell New York. I mean, it will be able to recognize the the stick of spelling, right? But it won't be able to recognize that we are trying to spell a word. Do you get that? I mean, there's this voice equivalent, yeah. So it will be able to return N, A, W, but it won't change them together. So
I
think
could be
that's
fine though,
something I
right?
want
Like,
to,
it could be
yeah,
fine.
it's actually fine.
Okay.
But it's actually fine, but I feel, this is supposed to be an application, right? So I don't know, how we might want to take care of that if this is being deployed in a real life environment. Yeah.
I mean, if you want, you could have a layer on top of your model that, whenever it gets a token representing a whole word, it outputs the whole word. And whenever it gets a letter, it waits until it gets all the letters, and then it outputs a whole token corresponding to all the letters. Or you just output the tokens directly. So like if you're dictating in someone's ear, you say like, I went to NEWYORK last week, something like that, which a human could understand pretty well, probably.
Yeah, but I think an additional layer you could do is even if one character is recognized wrong, because how it's spelled, you can like boost up the accuracy.
Yeah, spell correct.
Just because New is so common. That's really cool. Again, we can offer some compute resources. So
really? Oh, that would be appreciated if I did that. I mean, that's very stressful.
Also, annotation. I don't know. I know someone at Scale AI. They're an annotation company. Maybe they can do something. I can ask for you, but also people from the audience maybe they know some kind of tools out there that can make it easier. But what is your current pipeline? You just open each image and then you draw the bounding box yourself?
Yeah, that's what I've been doing. I draw the bounding box myself.
I see. Yeah, I'll see what I can do.
So also, Stephen, I think if you want to write a paper on this, you have SSD and YOLO results. You should compare it to a third method, which is just take the images and train a classifier. From the whole image, just output the class, where the class is whatever sign. Does that make sense?
Okay. You mean I shouldn't annotate the images? I should just, train them on a classifier. Is that what you're saying?
Yeah, so take the same images. So your annotation is a bounding box and the class. So what I'm saying is throw away the bounding box, just use the class and train it as a classifier, and compare that to how well the bounding box version does. Because if that version works better, that actually suits your purposes as well. Like you don't really need to locate their hands in the image. You just need to say what word it is. It would just be good to see, does that work better or worse with the same?
Oh, okay. All right. I'll try that out. Thank you.
Yeah,
I didn't.
One object.
I just assumed that.
Since there's only one.
I didn't get that.
Oh, I was saying since there's only one object in each image, you can also just take the bounding box. You have to do some rescaling, so it'll be nasty, but you can also do the same image classification procedure, but just taking whatever is inside the bounding box, just as a baseline.
Oh, okay. Okay. Thank you. And yeah, I'll try that out.
Yeah, that would also show you some validation whether the model is looking at the background. Like when you say sometimes when you say I love you, it's in front of your chest. Sometimes with other signs is next to your head or something. You can see the model is actually using those information to make decisions.
Oh,
also,
yeah.
I think submitting this to, like you mentioned, the workshop, I think that's a great idea. I think it would be quite appropriate. In addition to submitting somewhere, I think it'd be really cool if you made a demo where you just have a single video playing and you annotate every frame. Even if it's not live real time, you can just annotate the frames separately and put it together in a video. But then I think that'd be just really cool to see, like someone signing and like your model is recognizing hopefully the keyframes and like outputting the words that they're saying. I think that'd be just awesome. It would make a great blog post too.
Oh, okay. I'll definitely try that out. I think the earlier model, I mean, the first build of this, I did something similar, but you know, the sign words supported were limited. I mean, it was only supporting 10 phrases. So, so I couldn't create coherent sentences. I could only perform, you know, all those signs, yeah, all the signs, you know, that were trained on the model. So now that, you know, the model is supporting a wide number of, a wide amount of sign words, maybe I could try, you know, recording a video where, you know, the model is recognizing full sentences. Thank you, Jason.
Cool. Yeah, that's awesome.
Okay. All right, so I guess that's all. Thank you very much.
So you're going to show a sign of thank you.
Yeah.
Oh, thank you. Well, this time it worked so well. I feel like maybe in the future research jams, we should just limit the interest to like less than 3. I feel like when we have lightning rounds, it's always hard to have in-depth discussions.
Yeah, I agree.
Yeah, and also we don't have to switch Discord for parallel discussions. We can just do all the discussions here. I think that's nice. Any more comments from the audience? If not, we can end early. It's really lovely to see you all, and thanks to all the presenters. Yeah, awesome work for sure. I'll be in touch with the compute resource for the 2 projects. I think Nigerian's team also already got support from us. And as you guys are writing papers, if you need any help, of course, the community is always here, can help you write, help you, review, and do all kinds of support if you need any. The community is here for you. Cool. Again, good to see you all. See you next time, or reading group this Friday. Bye.
Good to see you guys. Bye.
Bye.